Hello everyone. This video is in continuation with the lecture series in Basic Electronics EC 102. In this video we are going to study VI characteristic curve of a diode. Okay, VI characteristic curve of a diode. Now, what is VI characteristic curve of a diode? To understand the behavior of a diode when it is connected in an electrical circuit, we plot VI characteristic curve. It is a graph between the applied voltage across the diode and the current flowing through the diode. This is the practical arrangement for plotting diode VI curve. Now, what will we do? We will apply external voltage to the diode. If we want to plot the forward characteristics or the characteristics of diode in the forward region, we will connect the anode of the diode to the positive supply and cathode to the negative supply. Okay, now we have connected a resistor in series with the diode to limit the current flowing through the diode. This voltmeter is connected in parallel and this ammeter is connected in series with the diode to read the voltage and current values. We will take voltage on the x-axis or the horizontal axis as it is the independent variable, and we will take the current on the vertical y-axis. Now, why do we want to limit the current through the diode? Because every diode has a maximum current rating. If the current through the diode exceeds this limit, it may get damaged due to excessive heat. So, the maximum rating or ratings of a device should not be exceeded. Now, we have learned how to make the practical arrangement for plotting diode VI curve. This is the external applied voltage. The polarity of diode is such that the diode will be forward biased. So we will study what will happen when the voltage is very less in magnitude. When the forward voltage is very less in magnitude, diode will not conduct. The current through the diode is very less because the potential barrier across the PN junction seizes the electrons to cross the junction. Now, when we increase the forward voltage, VF stands for forward voltage. When we increase the forward voltage till the point known as cut-in voltage or threshold voltage. Threshold voltage, the current through the diode is very small. When the forward voltage becomes equal to the cut-in voltage or threshold voltage, the applied voltage will overcome the barrier potential and you will see the current starts increasing rapidly. We can say that now the diode is conducting and the current through the diode is significant. So this curve is for silicon diode and we have plotted this curve at room temperature. This cut-in voltage is equal to the barrier potential. The barrier potential depends upon three factors. One is the type of semiconductor material, other is the temperature, and The third factor is a type doping. Yes, the third factor is doping. On these three factors, barrier potential depends. For silicon diode, this barrier potential is zero, assumed to be 0.7 volt. Because of the manufacturing variations, we say that the barrier potential of silicon is around 0.6 volt to 0.7 volt. If we take a germanium diode, its barrier potential is assumed to be 0.3 volts. Okay, so it depends upon the type of uh, semiconductor material and room temperature. So this curve is for silicon at room temperature. Now we can say that when the how can we define cut-in voltage? Cut-in voltage is the forward voltage at which the current starts increasing rapidly. It is equal to the barrier potential of the diode. For silicon, it is equal to 0.7 volt. Okay, now the current increases exponentially. So we can see that diode is a non-linear device. It will not follow the Ohm's law. Here the current is not directly proportional to the voltage. We can see that for a very small change in voltage after 0.7 volt, if we further increase the applied voltage across the diode, then we can observe that for a small increase in voltage, there is very large change in current. Now we cannot increase this current beyond the maximum current rating of the diode, otherwise breakdown will occur. Now this is all about the IV curve in the forward bias region when the diode is forward bias. Now we will study what will happen in the reverse bias. To plot the characteristics in the reverse bias region, what will we do? We will change the polarity of the diode and this ammeter. If earlier we were using it to be milliammeter, now we will use the microammeter. Okay, because current in the reverse direction is very less in magnitude, microammeter or in the range of nanoammeter. If we are using a germanium diode, it will be in the range of microammeter. If we are using a silicon diode, it will be in the range of nano ampere. Okay, nano ampere. Now here I've written IF stands for forward current. Its range is in milliamperes, and IR stands for reverse current. It is in the range of, for silicon, it is in the range of nano ampere, or you can also write micro ampere. Now, when the diode is reverse biased, very small, excessive small amount of reverse saturation current denoted by I0 will flow due to minority charge carriers. Barrier potential helps or assess these minority carriers to drift across the junction. But this current will be constant because number of minority carriers is independent of the voltage. It depends upon the temperature. As we are doing the analysis, we are plotting the curve for at room temperature. Temperature is constant, so number of minority carriers will also be constant. So a constant reverse saturation current will flow. So when we apply a small reverse bias voltage, a very small, excessive small amount of current known as reverse saturation current denoted by I0 will flow. But what happens when we increase the reverse voltage beyond a point known as V, sorry, V not able to select it right now, it's okay. V B R. This is known as breakdown voltage. When the reverse bias voltage increases or reaches the breakdown voltage, what will happen? You will see that current increases by a extremely large amount, and because of excessive heating our diode may get damaged. So this is the breakdown voltage. The breakdown mechanism, there are two breakdown mechanisms possible in a diode. One is avalanche breakdown and another is Zener breakdown. When the breakdown occurs at a reverse voltage greater than 5 volt, it means avalanche breakdown mechanism is dominant. And when breakdown occurs at the reverse voltage less than 5 volt, it means Zener breakdown mechanism is dominant in that ordinary diode. So we can say that the what we can say about the reverse bias characteristics of a diode, like initially when the reverse bias voltage is small, then a very small amount of reverse saturation current flows, but when we increase the reverse bias voltage and till it becomes equal to the breakdown voltage, then the current becomes very large in amount, and typically breakdown voltage of an ordinary diode is around 50 volt. Okay, so VR stands for reverse voltage. This is about IV characteristic curve of a diode. So we can say that a diode, practically we can say that a diode can be replaced by a 0.7 volt battery when the applied voltage across the diode becomes equal to 0.7 volt. Further, if we increase the external voltage, we can see that there is no change in voltage or forward voltage, or very slight change in forward voltage, but there is large change in current. So we can replace it with a 0.7 volt battery. Okay, now we will study the temperature effects on VI characteristic curve of a diode. How temperature affects the forward bias characteristics. If we study in the forward region, we can see that the curve shifts to the left. Curve shifts to the left. What does it mean? At 25 degrees centigrade, at room temperature, then above 25 degrees centigrade, this curve will shift to left. It means that for a fixed value of current, if I draw a perpendicular to the current axis, and then I can say that for a fixed value of current, voltage will be reduced. So here voltage is, if here voltage is V1, now at temperature above 25 degrees centigrade, voltage is V2, which is a reduced value. So for a particular value of current, voltage will get reduced. So we can say that cut-in voltage will be will get reduced at a higher temperature. Cut-in voltage or threshold voltage or knee voltage reduces 2.5 millivolt for every 1 degree centigrade rise in temperature. Now, for a fixed operating voltage or fixed forward voltage, if I draw a vertical line in the upward direction, I can see that the forward current increases. Here forward current is of this amount, but here forward current is this much. So at a higher temperature, forward current increases, cut-in voltage decreases. Now, what are the effects in the reverse bias region? In the reverse bias region, as the temperature increases, number of minority carriers increases. So above 25 degrees centigrade, reverse saturation current increases. Now what about the breakdown voltage? This breakdown voltage may be increased or may be decreased. It will depend upon the breakdown mechanism, which breakdown mechanism is dominant. So when the Zener breakdown effect is dominant in that diode, then the breakdown voltage will be increased. So as we can see in this curve, the breakdown voltage will be decreased. Breakdown voltage and at above 25 degree, the value of breakdown voltage will be decreased in case of Zener breakdown effect. And here we can see the avalanche effects, which is where breakdown voltage is having positive temperature coefficient. Here, when the temperature increases at 25 degrees centigrade plus delta T, we can see that breakdown voltage increases. So this is the value of breakdown voltage at 25 degrees centigrade plus delta T. This is the value of breakdown voltage. This is the value of breakdown voltage at 25 degrees centigrade. So we can see here breakdown voltage increases. Breakdown voltage has positive temperature coefficient, but because here avalanche breakdown effect is dominant. When Zener effect is dominant, breakdown voltage decreases. So this is all for today's lecture. Thank you so much for patient hearing.